Well, hello everyone. Welcome back to Adrian's Digital Basement. If you're like me, you probably have a bunch of retro computers in your own collection, and this particular hobby seems to involve a lot of constantly trying to keep everything working. It's actually one of the reasons why I even got into this hobby, and I realized that I really enjoyed it, was partially the nostalgia of using these old fun computers, things I always wanted when I was a kid, but also the challenge of keeping everything running. Stuff seems to break a lot, and if you watch the channels, you'll see that I have a lot of broken stuff. Well, recently I was going through my floppy drives, and I was looking at old full-height 5¼ drives just like this. This one is actually a
single-sided
Tandon unit that comes out of an IBM 5150, so this drive is over 40 years old. And even though these types of drives are very reliable and generally work, this one has a fault. While the mechanics of the drive, spinning the disk and clamping the disk and moving the head around, those things all seem to work, it doesn't seem to be able to read any disks. So in this video, I want to dig into the electronics here, figure out if the problem is the read-write head or the electronics, and if it's the electronics, we can try to fix it. So without further ado, let's get right to it. For today's repair attempt, I'm not going to use a DOS PC to access this floppy drive as I normally do. I'm going to be using this. This is a Greaseweazle, which is an open source floppy flux imaging read-write tool that you can plug into your modern computer, Mac, Windows, and Linux compatible. And what's awesome about this, besides the fact that it's open source, is very inexpensive. And you can plug it into your old disk drives for both diagnostic purposes like we're about to do today, but also to read and write images, format disks, check the RPM, clean the heads, and, well, other disk drive type functions. I've been meaning to make a more in-depth video about the Greaseweazle because I think this is just such a fantastic project. I actually keep one of these permanently plugged into my lab computer here with a 360K and a 1.4 meg disk drive, which allows me to read and write pretty much everything I need to without having to, well, leave the confines of a modern computer. It's awesome if I'm working on like an old Apple II over there and I need to make a boot disk. I can just quickly do that in seconds using the Greaseweazle on my Windows 10 lab computer here, and then I'm up and running on the Apple II. It's absolutely fantastic. But that's not the focus of today's video. Let's get back to this disk drive. So the floppy drive in question, it is a very standard issue full height floppy drive. You've probably seen these on many old computers. And this is, of course, a Tandon TM-100, which is a replica of the Shugart SA400. The SA400, designed by Shugart, was the first 5¼ floppy drive, I think, ever, actually. The original Shugart drive has this front faceplate, which you've undoubtedly seen on many, many other disk drives because everyone just blatantly copied the design of the front faceplate. You can tell that this one is a Tandon drive if you remove the little protective card here, because when we flip this like this, you can see right here it says 48 TPI SSR. That's something that Tandon did, and I don't know if other disk drive manufacturers also did this, but that's a nice thing about Tandon. So you can quickly see, without having to take the drive out of the machine, how many tracks per inch the drive is. And that's pretty important because on a 5¼ disk, you actually have 3 different standards of tracks per inch. And because the magnetic media is just a disk with a bunch of iron oxide on it, the way the tracks are laid down onto it is pretty much arbitrary and is defined by the disk drive itself. The 3 common track per inch parameters are 48 TPI, which is a 40 track drive like this one, or 35 track, or 40 track, same thing. There's also a 96 track per inch drive, which is 80 tracks. And then you have a 100 track per inch drive, which is also 80 tracks. But if you can imagine 96 track per inch versus 100 track per inch, they're similar, but not the same. And if you have a disk that was written on a 100 track per inch drive, you cannot read it in a 96 track per inch drive, or of course you cannot read it properly in a 48 track per inch drive. You'll notice this faceplate has IBM branding on it, and it's because IBM partnered with Tandon to put these disk drives into the very first IBM PC. And if you flip this over, you can see right here, TM-100-1A. Now there are different variants of these drives, and off the top of my head I can't remember all the different variants, but they're all TM-100, but then the dash and then the number that's after the dash is what matters. They actually make 96 track per inch versions, 100 track per inch version, double-sided, single-sided versions of all of the drives as well, plus the 48 track versions like this, which can come either in single-sided or double-sided. Without even looking up the model number or taking this drive apart, you can tell it's a single-sided drive because there is only one read-write head attached. Strangely enough, the PCB seems to be fully populated for a double-sided drive, but physically, this thing only has one read-write head on it. One little tidbit about the Tandon TM-100 drives is that the front lever here, which you push into, well, release the disk so you can get it in and out. Due to a design flaw with the original plastic clips here, this thing breaks and there's really no way to fix it without 3D printing an entire replacement part. I made a video about doing that because I've had multiple of these drives break, and frankly, I'm completely flabbergasted that this one is still in one piece, considering the age of this drive, having come out of an original IBM 5150. IBM only used a single-sided variant of this drive on the 5150, and I think they actually ended up switching to using double-sided drives on the later versions of the machine. So this must be a somewhat early machine or early drive. Let's just see if we see anything on here about a date code. Often there's a stamp on these drives that indicates when it was manufactured. And there it is, April 25th, 1983. A little bit later than I would have thought, to be honest. You do have to realize that contemporary machines to the IBM PC were all also single-sided, the Commodores and the Apples and pretty much everything else. That's probably why they originally went with the single-sided drive here. The PCB on the top of the drive specifically handles the disk interface to the host computer. This is the Shugart standard that they came up with in the SA400. It has all the circuitry on it to read and write from the read head. So this is of course very low voltage, and it has to have amplification for reading, and then for writing it has to turn on the erase heads plus do some biasing. Not to mention this also handles all the stepping of the read-write head assembly and turns on the drive motor when the drive select signal comes in from the host interface. Unlike later 5¼ inch disk drives, even ones in this same form factor, but especially half-height ones and whatnot, this does not handle speed control for the disk itself. That is handled by a little PCB attached to the back of the board here. This actually connects to the motor here, which is what drives the main spindle, and it's got a tachometer signal that comes into here as well, so this actually has a speed controller, and you can adjust the speed using this potentiometer right here. Really, the only thing that comes from the main PCB is a signal to just turn on or stop the motor. Now, I won't get into too much about servicing this disk drive. I think I've made videos about it before. It's pretty simple. You just take it apart, well, take the board off here, and you can just take these two screws off, and then you release the read-write head here, and you slide this back so you can kind of get this out like that, and now you have access to all of the mechanics. One of the only issues I really ever run into these things is the head just sort of gets stuck a little bit because the lubricant on these tracks just dries up. So a little bit of cleaning, a little bit of oil on those tracks usually gets these things working again. Now, because it's a single-sided drive, this thing right here is not actually a read-write head, even though it looks like it has the capability to be one. See all these little guides here for wires and that little space there? I think a head could go into there and then the wires would come off just like this one here. But instead it has a little square piece in there with a little foam pad, and that pushes down on the disk, and that's it. This lever is the stop for the little spring there, which gives the correct amount of spring tension to push down the pad onto the disk, because without a little bit of pressure pushing the disk onto the read-write head that's on the bottom of the drive there, it wouldn't be able to read it at all. So with a disk drive like this that doesn't read and write, one of the first things you want to check is that the pad is there, and I can see that it's there and it looks completely fine. If that were missing, I'd have to try to recreate it somehow. If the spring were missing from here as well, that would also pose a problem. That would just have this flop around, and even if the pad were there, there wouldn't be enough pressure to push down on the disk, so nothing would be read. But everything seems completely fine, at least with this disk drive. The next thing to consider are the connections here from the head into the drive controller. Everything seems totally fine here. I'm looking for any kind of frayed wires or things that are pulled out, but this all looks completely without issue. Now, I've worked on enough of these drives to know that it's this connection on the left side here for the lower head, and this is the connection for the upper head. The next thing worth doing is just physically inspecting the PCB here and looking for anything that's obvious. Maybe something fell onto the disk drive, or maybe someone was inserting a drive above it, like they were stacked, and they hit this and they knocked some of these components off. Well, you know, I don't think that's the case with this disk drive. Everything looks perfect here. This drive is very clean. I don't see any kinds of issues of any kind. This is the configuration block here, allows you to set up some of the drive stuff. And this is the termination resistor pack. The Shugart floppy drive standard that all PCs use, and pretty much most computers except for things like Commodores and Ataris, has to have some termination, at least somewhere on the chain of the disk drives. Typically, you'd want to have it on the last drive on the chain. You can have up to 4 disk drives, and if you have a long ribbon cable, you want the termination at the end. The controller also needs termination on it for everything to work, but what the drive terminates and what the controller terminates are different. All the signaling that happens between the floppy drives and the host computer happens over a bus that's pulled up to 5 volts by these terminating resistors on the controller and on the disk drive. And then all the signaling happens by open collector drivers, which are 7406s typically, at least on old things like this. And what those chips do is they'll take that 5 volt signal that's pulled up through these resistor packs and they'll pull them down to ground. And that transition from 5 volts that's always there because of the pull-up resistors down to that ground when a signal is being sent is what allows the drive and the controller to know that there's a signal that's active on the bus. If you don't have any termination resistors on the bus, say that this was the only drive and this was removed, then what would happen is those signals that this is normally pulling up to 5 volts would just be floating potentially around 0 volts. What happens is the drive is not going to receive those signals because you're not going to see that nice transition from 5 volts all the way down to ground. You're just going to have a signal that's mostly around ground anyways, and therefore you'll have something that doesn't work. Well, you may be wondering why modern disk drives like 3.5-inch floppy drives don't have any kind of termination resistors or a jumper even to set that. They just seem to always be terminated, and you can connect them 1 or 2 and it doesn't seem to matter. Well, originally with these drives, they were using 150 ohm termination resistors because the idea was you would have a very long cable with 4 drives on it and a host computer, and you needed a lot of current to be able to push through the interference that might be on the cable. Well, when you're using short floppy drive cables inside a PC case and only 2 drives, drives started implementing their termination resistors around 1000 ohms, I think, and they're just always enabled. If you parallel 2 of these together by having 2 drives terminated, you're going to end up with 75 ohms. That means those 5 volt signal lines are pulled up with 75 ohms. That's a lot of current that you have to fight against if you try to pull those down to ground. In fact, 75 ohms is probably more than the drive controller is able to pull down to ground, so it actually will result in a non-working system as well. And it might actually cause some damage to the controller side. It's exceeding its current capability. But with 1000 ohm resistor packs on those 3.5-inch disk drives and later 5.25-inch drives as well, when you parallel those up together, you're at 500 ohms, which is still less current than the 150 ohms that was on this original pack. So all the controllers can handle 150 ohms, and anything higher than that is totally fine. If you ever get a drive like this, a Tandon drive at least, and you don't have this resistor pack in here and you need to use the drive because without it, it's not going to work unless you have another drive on the chain that is terminated. All you need to do is take some resistors and connect them from that pin to that pin and that pin to that pin and so on and so forth. And you can use 150 ohms, you can use 1K resistors, any of those should work fine. The reason why I'm kind of going through all of this is because this drive, as I mentioned, when I tested it, and we'll test it in a second, it wasn't able to read any disks at all. So when you have a problem like that, it's always good to just kind of go over all the possibilities first, like is the head connected, is the pressure pad installed, and is the drive terminated properly. On this drive, it appears that all of that stuff looking good, and nothing physically looks damaged on the board, everything looks fine. So the next step is, let's hook up the Greaseweazle and grab a known good disk and see what's going on exactly. If you're thinking about getting a Greaseweazle to hook up floppy drives to your modern computer, make sure you have the necessary accessories to actually connect your drive. You're going to need a power supply to power the drive. There is a little power connector on here. I'm not exactly sure what that's for. This thing hooks to the computer via USB. This particular version just has a USB-B jack on it. There are other variants that have micro USB and maybe some newer ones that have USB Type-C. And of course you need a floppy drive cable. This is one I've had for a long time, and I think I moved one of the connectors off of it or around it. So there are some holes in the cable right there, hence the tape. But this particular cable is long, which is why I like it. And it has both the edge connectors and the pin connectors necessary if you're going to be connecting up 5.25-inch floppy drives like this one, or more modern 3.5-inch style disk drives there. The twist that's on the cable was originally added by IBM to allow easy connection of 2 disk drives to the PC without having to modify any jumpers or settings on these drives. Having a cable with a twist with the Greaseweazle is not necessary because it can support 2 drives using the straight through cable, or it supports using the twist. It's a very flexible device. You can download the Greaseweazle software from the repository, and you can see right here, this is a Greaseweazle version 4, and it auto-detects the COM port, so it's pretty nice, although it makes it a little bit more complicated if you have 2 Greaseweazle connected to your computer at the same time. Now, when I first hook up a floppy drive to the Greaseweazle and I want to start doing testing, one of the really useful utilities or parts of the program here is the clean option. It's designed to move the heads around in a way that helps you clean them if you have a cleaning diskette inserted. But I also like it because it kind of exercises the disk drive and also tests to see if it's communicating to the Greaseweazle properly. The one thing about the Greaseweazle suite though is it seems to default to 80 tracks, and with a 40 track drive like this, if you try to use the clean utility without specifying that this is a 40 track drive, it will error out. So you just do GW clean cylinders 40 and we hit enter, and now the drive is doing its thing. You can see if I flip it over, it is spinning, the light's on. In fact, I'll unplug the head so we can flip the controller over, because while it's connected up, it can run like this. See, the head does this pattern where it goes back and forth a bunch of times, perfect for if you insert a cleaning floppy. If you have one of these old disk drives that has heads that are stuck, once you get the motor and the tracks lubricated, then it's actually perfect to use this utility to exercise the entire thing. And I use the passes parameter here, and you just put in like 99, and it will go through this entire cleaning process 99 times. I wouldn't recommend leaving a cleaning disk in there for more than maybe 3 passes, but if you're doing this testing, you can insert a normal floppy disk like this, and that really exercises everything on the drive. The spindle, because it needs to spin the disk, so all the torque of that is required, not to mention the whole head movement assembly. It really kind of gets everything warmed up and lubricated. Now I want to demonstrate something. If your heads are having trouble moving, I'm just going to forcibly stop them. There we go. I prevented it from going back to track 0, and it detected that right away, and it says fatal error, track 0 signal absent after seek to cylinder 0. What can happen after you get that error too is if you restart the cleaning process, you actually get these errors here and you're like, hey, what's going on? This happens because the Greaseweazle actually keeps track in a state table where the head currently should be. But since I stopped the movement with my finger, that state table is out of sync with the actual head position. So the way you get around that is you just run the GW reset command, which just resets the state table. It makes the Greaseweazle not know where the heads are. So when you start any kind of operation, it's gonna seek the heads to track 0 first. And you'll notice when I hit enter, there it is, it went all the way to 0, and then it starts running the process again. Now what this whole thing is telling us here is that the Greaseweazle is obviously actively communicating with the disk drive, and it's working both directions because this is sending commands to seek the head, and then if it reaches track 0, there's actually a little switch in there, and the drive signals back to the Greaseweazle, hey, we're at track 0. If there were any kind of termination issues with the drive or the termination that's on the controller itself, this communication wouldn't be possible, and you wouldn't be able to even do this seeking exercise that we're doing right here. All right, the next useful utility to check out is the RPM utility. And normally if you just run this, it's gonna do a quick test of the RPM and then it returns the drive RPM very quickly. Now you have to have a floppy disk in there because it's using the index sensor to sense the RPM. So if I flip that up and we run this, it's just gonna say no signal or something like that, no index. But what's cool is you can do a long-term RPM stability test, or if you just want to keep the drive motor running on your drive for a long time, you can use the -NR flags, and then you just put in the number of times that it's going to sample the RPM, and you just hit enter. This multiple RPM testing is perfect. If you're going to try to adjust the RPM, you can adjust the potentiometer on the back of the drive here, and you can do that in real time and see what you're doing. When diagnosing reading problems like this drive has, it's always a good idea to check your RPM just to make sure that it's pretty close to 300 RPM, which is what it should be for drives like this. If it's way far off, it's quite possible that you're just not going to be able to read the disk simply because the disk is running too quickly or too slowly. So we've established that the communication over the floppy cable here from the Greaseweazle is working properly. The termination is all correct, the index sensors are working, the motor control signals are working, all the head stepping assembly seems to be working. Let's try reading a floppy disk. Now for testing the reading on the drive, I went ahead and formatted this floppy disk on my DOS PC back there as a 180K single-sided disk. It's a known good drive, known good floppy disk, so testing in this drive would be easy. But the thing is, if you don't have a whole bunch of floppy drives or another computer that has a working floppy drive, we have to figure out a way to try to create a disk in the drive itself that we can then try to read back and see if that works. Unfortunately, there are 2 problems with that approach. One of them is that the drive itself may be out of alignment, and that means that it would have trouble reading disks made on other computers, But if we formatted a disk in itself, we should be able to read it back. Let's imagine for a second though, we don't have another floppy drive, so I'm gonna stick this disk, which I wanna format, into here, so we can then try to read it back. Now the thing about Greaseweazle is it's really designed to read and write to floppy drives, and it doesn't have a format command per se. It has an erase command, which you're looking at right here, but that doesn't actually lay down any kind of format on the disk. That simply just erases it. It's not quite the same as using a bulk eraser on the disk itself, but from my understanding, I think it's just writing a pattern, a simple pattern to the entire surface of the disk using the read-write heads on the drive. So for using a Greaseweazle to format disks, what I went ahead and did is I used WinImage to create some blank DOS disk images of various sizes that I can then just write onto the floppy disk, which has the effect of erasing, writing, and then reading back the disk to ensure that you have a good floppy disk. I wrote little batch scripts to help me with the command line parameters of all these things, and this is the one I'm using here to format this disk. So essentially just resets the Greaseweazle, and then it writes the blank 180 image onto the floppy disk, and you can see -- format 180, so that's telling Greaseweazle that the parameters that the disk drive needs, 40 tracks, single-sided, are already set up, drive A, and that's all we have to do. So we go format 180, and we hit enter, and here it is going to write to the disk. And immediately we get a fatal error, failed to verify track 0.0. So we can show an actual success with this format command. I've grabbed another floppy drive that was just sitting here off to the side. I think this is a 360K drive. Let's pop in this disk into here, and we'll just move the interface cable over to here. Hopefully this thing's already configured as a PC disk drive. And let's hit enter on here. Okay, there we go. This is how it's supposed to work when the drive is actually working. Thinking about what could be wrong with the Tandon drive, there are really two possibilities at this point. It could be that it's not able to write to the disk at all, so therefore the read phase of that format that I was doing fails. But one thing we'll be able to do is if we just take the disk out of here and switch it back over to this disk drive, move the cable back over, and now let's try to read this disk that we know I just formatted successfully in this other drive. If we hit enter, I have another little batch file here to help me do this. And what this script is really doing is it executes the Greaseweazle read command, but it takes a command line parameter, which is %1 in this case here, and it will save that disk image onto the D drive. I have that hard-coded. Format IBM 180, drive A, revs 1, I think that's number of revolutions per read. And then there's a retry parameter as well. So if the disk you're reading isn't working super well, you can have it read multiple revolutions and try to get a good read. But then of course there's also a retry, which causes a reseek of the head, and then it will retry the read. So we're gonna run this command, read 180 with a test180.img file. And here we go. So right off the bat, you can see here, it's not reading anything at all. 0 fluxes in 0.0 milliseconds. If there were any flux transitions that were coming in from the drive controller to the Greaseweazle, we would see those as fluxes here. Again, I'd like to demonstrate what it looks like to read a disk properly, so we'll switch the cable back over to the other disk drive. And switch this disk back over here. And we'll run the same command again. There we go, it goes very, very quickly. 47,240 or so fluxes in 200 milliseconds, which is, I guess, 1 revolution at 300 RPM. When Greaseweazle finishes up, it gives you this nice little chart here with the cylinders and then the sectors that it's read, and any kind of errors that have appeared will show up as little boxes in here. I think there's numbers that print. Let's switch over to the disk that I made on the other computer back there with a known good disk drive, because I actually don't know for sure if this floppy drive works. And we'll do that same read again. And what we're testing is the floppy drive on the left has good alignment that's able to read disks out of machines that I know have good disk drives that can read every 360K disk. And yep, looks perfect, no errors. Now what I'm actually curious about is maybe there's a way with Greaseweazle for us to write to this disk without verifying the write. And then what we could do is take the disk we made in this and put that into this known good floppy drive here. And that will allow us to see if the writing is actually working on this. And taking a look at the parameters available for the write command, which is what we're using to format the disk, no verify. I think that's what we want right there. So I'm going to copy this command line right here, and we'll add in no verify. Plug in the cable here. I already have the power on the drive, and hit enter. Let's see what happens here. Okay, so it's attempting to write this disk, and I'm really curious now to see if this can actually be read in this drive here. Let's move this over to the other drive here and move the disk over as well. All right, we're ready to do the read. Do you think it's gonna work? I actually have no idea what's gonna happen here. All right, well, it is working, but I just realized something. What if the Tandon drive isn't even erasing the disk, and this disk was already formatted before, and maybe it didn't even touch the disk, and it's just we're reading what was already formatted on there before with this drive. So let's use the erase command to erase the disk that's in the working drive here, and then we will try reading it back. Oh, it goes very quickly when it's doing this, and I want to see what happens when we try to read it back now after we've erased it. So here's the read command now. Yeah, so this obviously is not able to read this disk anymore. Notice it has like a small number of flux there, and it's stuck on track 0 still. So this is perfect. Let's slide this back into this drive and move the cable over. And we'll do that write command again with the no verify specified. Looks like we have to do the reset command first. And let's do that again. Let's go back to the other drive, the working drive. Move the cable over. And here we go. Let's read the disk. It freaking reads. That means the Tandon drive is able to write to the disk properly. It just can't read the disk back. And we've also confirmed that the alignment of the heads on this are fine as well. And to be honest, I've never had a drive like this that was out of alignment, especially on PC disk drives. There's no head banging that really goes on because it has a track 0 sensor. So 100%, this drive is able to write to the disk properly, the alignment is good, and this drive is able to read them. This drive simply can't read anything back off the disk. Now that's actually really good news, because on these types of disk drives, there is not a separate head for reading and writing. It is the same head that does reading and writing. There is a little separate coil in the head for erasing the disk that is turned on whenever you have the write signal enabled. But if the part of the head used for reading and writing were damaged or open, then this wouldn't be able to write to disks either. But it obviously created a perfectly good disk that this other drive had no trouble reading. So that kind of tells me that the issue has to exist in the circuitry on this board, and it's nothing to do with the physical connection here or the heads itself. It's something in here. Now imagine that hypothetically you're working on a drive like this that you don't have service information for. Luckily for me, there is a service manual for this disk drive. Tandon was such a well-known big company that they made service information for their drives. Shugart, of course, also did the same thing. So that means it's pretty easy to do troubleshooting and repairs on these types of drives. Lots of other drives, though, don't have any service information. Luckily, though, the fundamentals of how these floppy drive works are all very, very similar, and most of them pretty much copied everything that was going on with that first Shugart SA400. And the only big problem you can run into fixing these floppy drives is that much later versions of these drives integrated a lot of the discrete ICs and components into single application-specific integrated circuits, ASICs. And if you have a drive like that, I would say there's very little chance of being able to fix any kind of issues on the main board. Lucky for us, though, we don't have any of that going on with this drive. Not only do we have service information, but everything on here is completely off the shelf. It means that fixing this is totally, totally doable. Let's think about what components on this disk drive are working, and those are all things we can rule out, so we don't even have to focus on those. We know the stepper assembly is working properly. We were able to format a disk without any issues. We know the speed controller is working properly, and all the motor control signaling stuff, that's all good. We know the track 0 sensor circuitry is working fine because Greaseweazle reports if there's a problem with that, like when the head wasn't up against the stopper. We know all the termination is working properly, and we know that the write circuitry, that's the signals that come in from the ribbon cable and the Greaseweazle, make their way through the disk drive, through the right amplification and bias circuitries to actually successfully write to the floppy disk. That means that we have this connected to the right place, and the heads themselves are almost certainly working perfectly. Floppy drives that use the Shugart standard like this default to read operation all the time. When you select a drive and you turn on the motor and it starts spinning and you have the disk in there and the lever is down, it's reading data, and it should be coming out over the ribbon cable at all times. When you go to write a disk, which we know works, a signal comes in from the controller and it essentially switches in some circuitry and turns on the erase head that then writes the data that's also coming in on a different signal on this cable to the disk itself. That's all working properly. But when we're reading a disk, the information that's read should come in from the read-write heads here and make their way through some differential amplifier somewhere on this board, and then some magic happens to those analog signals that get turned into a digital signal and fed through the read pin on this connector back to the controller. There's obviously something going on in that chain somewhere that's preventing that signal from making its way back to the controller. I just mentioned a couple key points that are important for troubleshooting read operations. Remember how I said, as long as the disk is in there and it's clamped and spinning, the disk drive is going to be reading data off the disk drive. It happens all the time whenever the drive is spinning. That means if we're going to use an oscilloscope to probe around on the board, we only need something that can select the disk drive, which means turns on the LED and gets it spinning. And remember when I showed that RPM testing? That is exactly what that's doing. The RPM test itself simply looks at the index signal that's coming in from the index sensor and it's sent over the ribbon cable. But the drive is selected and the read-write heads are touching the disk and the disk is clamped. Therefore, we should be seeing data coming out of the disk drive going to the Greaseweazle. If you're ever in doubt about anything to do with the floppy drive system used on PCs or any of these other computers, refer to the SA400 manual from Shugart. Since they invented this disk drive format, basically everything that applies on all of these disk drives, no matter what the brand, is documented within this manual. And here's our relevant diagram. SA400 is the floppy drive itself, and host system is the Greaseweazle in this case. The Greaseweazle sends the motor on signal and the drive select signal, and that selects the disk drive and turns on the LED. And when those logic signals are valid on the disk drive, then the disk drive, as long as the disk is clamped, it's going to start sending read data back from pin 30 on the disk drive back to your controller. It's only when the write gate signal is asserted from the controller that the disk drive switches into write mode, and then the write data signal itself is then written onto the floppy disk. Probing these signals, Tandon is really nice, and they actually have the pins numbered on here. It's 2 there and 34 on this side. And of course, it's even and odd. So we're looking at the even ones here. So pin 30 is going to be this one, 3 in from the edge. This disk drive happens to have test points all over it, and that pin right there is grounded. So let's start the disk drive testing for RPM. I have that same formatted disk in here. And the oscilloscope is up. I have it at 1 volt per division because this is a 5 volt logic signal. And I am now probing pin 30. And we're just seeing kind of noise happening on there. Now I'm curious, if I take the disk out, does that change at all? No, not really. Well, it makes it stop testing for RPM because the index sensor went away. Let's check out pin 8, which is the index sensor signal, which we know is getting through back to Greaseweazle. There it is. If we zoom out a little bit, we should be seeing it. Yep, it's happening every 200 milliseconds, I think it is. Yeah, 100 milliseconds per division, so 200 milliseconds, which actually is another way you can gauge the speed of your disk drive if you don't happen to have a good tool for doing it. Now, one thing, if we go back to pin 30, that's actually quite curious. Why is this actually pulled all the way to 0 volts? It should only be pulled down to 0 volts while data is being transmitted, like there should be bits of information with it going up and down. If we take the disk out, I'm going to pull the power out of the power cord here. Let's see if that goes away. Yes, it does. So when thinking about termination and what's pulling the signal up to 5 volt, it's important to consider the direction. When you look at this diagram, the device that's pulling up the signal to 5 volts is the device that's being pointed to by the signal. So read, write, protect, track 0, and index sensor are all being pulled up to by the host controller, or the Greaseweazle in this case. And the SA400 with that termination resistor pack on it is pulling up any of the signals that point to it. So the drive select signals, motor on, direction select, step, write data, write gate. That means if there was a problem with that termination pack on the floppy drive and say one of its pins were broken off, it wouldn't affect the ability to read. It would affect one of those other things that's pointing to the disk drive. And it's also why when I unplug the power cable going to the disk drive, all of a sudden whatever logic on the floppy drive, it was grounding that particular signal, pulling it down to ground, goes away, and now the Greaseweazle is able to pull that signal all the way up to 5 volts like it would be doing in the normal idle state. Now I have a feeling when we go to look at the schematics, there's going to be quite a number of ICs in the path between the heads and the cable here. And it's not necessarily the very last thing in the chain that's the problem, although it could be. It's quite possible that some logic IC somewhere in the middle has gone bad, and that's causing the signal to be grounded all the way through to the cable. What I'm going to demonstrate now, I've plugged the power back in and put the disk back in. Let's restart the RPM test. I'd like to show that if you're trying to troubleshoot a disk drive that you don't have the schematics for, and you see test points all around the board like we do on this, it's worth probing around on those test points to see what kind of signals you see. Ah, okay. That looks like a read signal. So with MFM encoding, which is how this floppy disk is formatted with the DOS format, the zeros and ones are read off the disk, and I'm oversimplifying here, essentially with 2 different waveforms. So you should see one kind of sine wave change into another sine wave as the bits are read. Now if I take the disk out here, right away as soon as I open the lever, the signal goes away. So So there it's open, closed. That tells us that the read head right now is actually reading the floppy disk. And that's kind of cool. Now let's just look around at a couple other test points. So that was one that was right here in the corner. Here's another one right here. And there's a different signal, but it's also the read signal. And you see how it's changing frequency, modified frequency modulation. That's what MFM stands for. And opening the disk drive, and that signal just goes away entirely. Now what I wanted to demonstrate, and I'm gonna flip the controller just over so slightly, is I'm gonna try to lift the little pad that's touching the disk. I wanna demonstrate what that does, and I'm just doing it. I'm sorry I can't show it, but there I've lifted it. Notice the signal goes away entirely. And it's gonna be the same for this other test point over here that had a stronger looking signal. I'm just gonna lift it up ever so slightly. I mean, you can see I can modulate the signal by just lifting it ever so slightly. And that's the spring tension that I was talking about. If it's not enough, you're actually not gonna get any kind of signal read out of the disk at all. I'm gonna lift it right off the disk entirely. And there's a very weak signal there. You can just slightly see a sine wave, and I let go of that little pad, and there it is, it appears. Now if I push down on it a little bit harder, I don't wanna push too hard because it's actually rubbing on the disk. It doesn't really change anything. Now what you can see also, if I touch the spindle on the bottom, if I stop the disk, it actually goes away. And if I slow the disk down as well, you'll see the RPM at 225. Notice the signal amplitude also drops. So the faster the disk is spinning across the heads, the stronger the signal is actually going to be. So too slow of an RPM will result in no signal. Now this IC right here is an NE592. And without even looking at the schematics, I'm pretty sure this is a differential amplifier chip, and you're going to find this on a lot of disk drives. The read signal goes through this, and sometimes there are little adjustments you can do to adjust the differential amplifier, but this one doesn't seem to have those. And I think that's this output right here. Let's try this one over here, a little further up the chain. And that one doesn't really show anything. And I wouldn't be surprised if this has more to do with the write signal. If you're going to try to use your oscilloscope to see what's being written to the disk, I think that's what you're looking at here. You could ignore those little spikes we're seeing on there. That's just noise that's on my oscilloscope probes and stuff from improper grounding. What we definitely were able to see though is that this disk drive is reading the disk properly. The differential amplifier there is working, and we're getting a correct waveform. I've looked at enough floppy drives over the years to know that that waveform we saw there was correct for reading an MFM formatted disk. You're gonna see those types of signals when you're probing around on any floppy drive while it's spinning and actually reading the disk. That's of course if the differential amplifier is working and the read-write heads are clean and working properly as well. There is going to be some circuitry after that analog stage that turns that waveform into a digital signal. It does some kind of data recovery, and then that outputs a straight 0s and 1 digital signal that goes to your controller. A floppy disk is inherently an analog format, just like an audio cassette. And that means the waveforms that are written onto this are subject to degradation over time and if the disk goes bad. And it's those waveforms that we saw there that will get weaker and weaker and more difficult for the circuitry on the disk drive to turn into a digital signal that your controller can understand. And that's actually why there's quite a difference between one disk drive to another when it comes to the ability to read marginal floppy disks. I was actually trying to recover data off a marginal disk, and what I did is I went through all the different brands of disk drive I had, and I tried to read the disk, and I looked at the resulting flux image that was created, and there was a big variance from one drive to another when it came to reading that marginal disk. And I think that all goes down to the circuitry that's used for the amplification of the read signal and then the decoding and the declocking of that signal. How good is it able to discern the actual signal from the noise, signal to noise ratio? And there just was a big difference from one disk drive brand to another. So when I found that best drive in my collection that was able to read that marginal disk completely, I actually marked it as such and bagged it up. So if I ever have marginal disks that I'm trying to read that I'm struggling with a regular disk drive, I go and grab that disk drive, and then I usually can get a pretty good copy of the disk with that. And now, after all of this talking, it's finally time to take a look at the service manual for the TM-100. And thank you to everyone at BitSavers for posting this online, and it's such a good quality scan as well. The manual here is extremely comprehensive at 103 pages long. I'm just going to jump right to the end. Hopefully the schematics are here. Here they are. And we should be able to decode exactly what's going wrong on this floppy drive. So let's examine what's going on here. Head 0 and head 1 get connected into the disk drive here. And these are the two coils I was talking about. One is used for erasing and one is using for reading and writing. This is the floppy drive connector, and there are a couple signals that come in from it. One is the side 1 or side 2 signal, so there's going to be some circuitry to actually switch between the two different heads. And then there's a write data signal that comes in from the controller as well, which activates some logic, which does two things. It switches over to write mode, so it's going to output a signal to the head, but it also enables the erase heads. Now we know that the differential amplification for the read is working, and that's probably what's happening right here. So the signals come in from the heads. It actually comes in from both of them. See here, it actually splits off, goes into the differential amplifier. And if you look here, there's a write signal that comes in and makes its way up to this gate here, and that goes to the signals that go into the differential amplifier. And this probably just zeroes out the read signal, or the write signal for that matter, and it doesn't let it go into the differential amplifier. And you notice here there are diodes on the connections to the heads, and that's so that this signal that's zeroing out the inputs to the differential amplifier doesn't feed back into the head, which is obviously going to be trying to write the signal to the disk while the writing is happening. Well, we know that the writing works properly, so we can ignore all of that on the circuitry, but we also know that in the idle state, the heads are reading the disk. And that's because somewhere along here, like there's test point 1 and test point 2, I was connecting up and reading an actual signal coming through these differential amplifiers. In fact, the nice sort of equalized signal that we were reading there, that was this point over here, was test point 1, right there, feeding into this stage of the 592. And it was actually this test point over here closer to the front of the drive, and that's TP4. That had the stronger signal, the one I thought was pre-equalization and processing. But to be honest, that is actually after the amplification stage. So TP4 signal makes its way over here to this amplifier right here, and then that makes its way into this logic circuitry. And you see this logic circuitry here, and if we follow this, that makes its way to pin 30, which is the output going to the drive connector. So what we should do is probably look for this LS86, which is marked as component 5D. I don't know if this PCB matches exactly the schematic here, but pin 11 is the output of that. And that is the first place that we should start to see a digital type signal that then makes its way through the rest of this. Well, this chip right here is the LS86. That is labeled 5D on the silk screen, and it was pin 11 we need to look at on that. So I'm just going to slide the disk back in here. Oh, and interesting is the Greaseweazle RPM command seemed to have frozen, and I can't even Control-C out of it. Let's see what happens if I pull the USB cable. Well, that freed it up. Let's plug that back in. All right, and there's the signal right there. So that's that first digital conversion from the analog waveform we were looking at into some kind of digital signal. Let's turn off the AC coupling. We don't need that any longer. And zoom in here, and yeah, you can see sort of the bits are dancing around a little bit, and that is that conversion process. And if I open the disk drive with my other hand, it just turns into kind of noise. All right, so moving on, let's go further down the chain. Here, this is on the same IC again, 5D, but pin 8. So now let's bring up the oscilloscope. Aha, we no longer have a signal. So we're further along on the signal and we're not getting anything. So is this the IC that's bad? Since nothing is coming out of pin 8, let me just count my pins again. 8, yep, I'm on the right pin. Since we're not getting anything there, well, clearly we're not going to get any data out of the disk drive because it's stopped right there. So we know the output here is good. Let's focus on this chip here, 5E, on LS221. So the 221 is actually just a 74221, and I'm currently connected to pin 4. And yeah, that's not really looking very good, is it? There's kind of a signal there. We're at 1 volt per division, so we're like at 2.5 volts, and it just looks kind of terrible. Now, it could be the input to that chip that is causing the problem, the 74LS74 in 5C. And looking at pin 4 here, which is the output, it's obviously going to look like the same as the input to the other IC. So yeah, it looks the same. If I take the floppy drive out, yeah, the signal definitely changes. It goes from noise to that. And this is where it's tricky. I think the failure is in one of these two chips, but which is it? Let's look at pin 2. This is fed off an input that goes into the LS186. Let's see if that is stuck at that weird 2.5 volts. And no, that looks totally fine. That's the strong signal we should be seeing at 1 volts per division. So at this point, I'm not 100% sure which of these two ICs is the problem. I'm going to grab a marker because I'm pretty confident is one of the two chips here that has gone bad. Let's take a look at the data sheet for the 74LS74. So pin 1 is the clear signal for that particular unit, and pin 4 is the PR1 signal. Now, when it says high, I'm assuming it just means high, as in 5 volts. And we can test that really quick by just checking pin 1, and that's at 5 volts. And pin 4, yeah, also at 5 volts. Okay, those are fine. So pins 2 and 3 are the inputs to the flip-flop. Pins 3 being the clock signal, and pins 2 being the data signal. And then the other IC that's possibly bad is the 74221, which is a dual monostable multi-vibrator with Schmitt trigger inputs. Now there are actually 2 outputs per unit on this device. And this is actually similar to what we saw on the Plexus when I was troubleshooting the RAM problem on that. I was able to validate that one of the outputs was bad, but the other one was good. And the output that's being used in this case is pin 4, which is right there, 1Q. And you can see right here, 1Q with a line over it. The complementary output is pin 13, which is 1Q without a line. It doesn't look like that is actually connected to anything at all. So that's just free floating. So let's take a look at the output of that signal. All right, there's pin 13, not looking like anything is coming out of it whatsoever. And if we go back to pin 4, we get that signal there at like 2.5 volts. And let's just double check that the disk drive is generating a correct data signal. Yes, it is. I just wanted to make sure I'm still reading the right part of the disk. If the head moved off to like track 40, something that's not formatted, we're not going to get anything. So that's very suspicious that the output here, pin 4 and pin 13, aren't doing anything at all. And if you look over here, the other unit on 221 is being used, and I think that is actually going right to the output, or nearly to the output, to the floppy drive cable. Well, it is my assumption that's probably the 74221 that's the problem, because this complementary output should absolutely be showing a signal right now. And we know for sure that the input to this IC on pin 2, which is right there, looks correct. As far as I'm aware, that looks correct. And if we look at the truth table, when you have high, low, and then you have a signal that goes up, the output should be generating something. And without a doubt, it is not generating anything. Well, one of the lines is stuck at 2.5 volts, and the other one is just stuck, I think it was at 0 volts. Okay, so with that, I'm gonna say that this is the IC that is the problem right here, the 221. I'll just draw a line on it there. All right, so the next step, let me remove that IC, put a socket in, and then we'll try another one in here and see if this disk drive starts working. And just like that, the chip has been removed, a socket has been installed. I have a spare chip in my left hand here, which I found off an old board, I salvaged it. And this is the one that was in this disk drive originally that I think is bad. So let's install the one that came off the parts board. I don't know for sure if this chip works. It's not like I tested the parts board. There it is, easily enough installed. And now while this thing is just sitting here doing nothing, let's check the output on pin 4 with the oscilloscope. All right, well, there's a bunch of noise. And that might be fine actually, and that's because the disk drive is not currently running, which means that the output of differential amplifier is just a bunch of noise. So I'm just gonna move this window off to the side here so we can look at the signal as we start it up. There it is. I'm gonna hit enter. There's no disk in the drive. I was like, oh no, it didn't work. But let me put the disk in there. And let's try again. All right, there's definitely stability there to that signal. It's no longer just noise. Let's zoom in a little bit here. Oh yeah, that is a good signal. Well, let's just go right to pin 30 on the drive connector here. There we go. That was it. That was the bad chip. So now if we go over here and let's see if we can find that format command here. All right, there's a write command. We'll take away the no verify. And here we go. We're gonna format this disk. It's freaking working. It is freaking working. It was just this bad chip, 74221. What was this one? This was the Schmitt multi-vibrator something or other chip. So that format process went correct. I'm gonna take the disk I formatted in the other computer and let's try to read this. Here we go, read 180, test 180, hit enter, and here we go. I figure it's gonna work because it just formatted a disk correctly. It looks like we got a few read errors. It did read the whole disk correctly in the end, but I was touching this controller while it was reading. I just wanted to screw it in. Let's put these screws in here so this doesn't move around at all. All right, let's try that one more time without me touching anything. Look, it's still getting some errors here, actually. I'm still able to successfully read the disk, but at the end there, got some issues. It's quite possible that this floppy is bad, so what I'm going to do is I'm just going to quickly format this one in the other PC over there, and then we'll try to read this again. Okay, disk has been formatted in that machine right there. You can see the VGA monitor is turned on. Now these disks here were in my box of like untested disks, and it could be that this has marginal issues on it. Could be that this drive is marginal. If this disk that we're reading now, which has the blue label on it, has the same issue near the end here, ah, look at this. This thing still has some kind of issues. Very interesting. I wonder, is it the heads that are maybe dirty somehow on here? Let's give them a little bit of a clean. I have this cleaning disc here, which has a piece of plastic there, because you don't want to rub that little pad that pushes down onto the disc all over the cleaning media, right? This is very abrasive. So I have one of these for single-sided drives like this, or things on Apple IIs and whatnot. And then I have a different one, of course, for double-sided drives when there's two heads. So let's run the clean command on here. Okay, with that clean completed, let's go back to the disk I just formatted and try to read it again. See if this makes any difference. Now, one thing about this particular drive, these tandem drives, there's no adjustments you can do on the main PCB. There's no pots to turn or anything to adjust the differential amplifier. So this particular read error that's happening could be due to an alignment issue. If anything, it's actually worse. Still read the whole disk, but we had a few retries there. Like I said, this could be due to like a head azimuth issue. This also could be due to the RPM. You know what I'm gonna do? I'm gonna turn up the speed ever so slightly on the drive here. See how to best do this. Let's go a little bit above 300 RPM. Let's see if that makes any difference at all to the reading of the disk. Oh, this is the same disk we're gonna be reading. Didn't really seem to make a difference at all. And we're reading the disk again, and I have it connected to that test point here. I just want to see what the signal looks like as it's reading the bad parts of the disk, or the parts that it thinks are bad, at least. The signal is certainly getting smaller and weaker. Although notice this time it didn't actually have any issues reading at all, which is odd. Let's look at the RPM on track probably 39. That's track 40 basically. And I'm going to set these cursors here to the amplitude of the signal that we're seeing here. And now let's read the disk again. And we can see that as it starts reading, there's definitely a higher amplitude. But that's expected actually, and that's because the 5 1/4 inch floppy disks start reading on the outside of the disk, right, where the tracks is the biggest. And as you move towards the inside of the disk, there's actually less magnetic material and less speed passing over the head. And that means that signal that's being picked up is just a lot weaker, and the amplitude therefore is less. Let's move to that other test point, which is this one that's before that second stage of the differential amplifier. And we can see that it's pretty low. Let's set the cursors here as well. I want to see how much this one changes as we read the disk. Okay, so there we go. That's a little bit more intense at the beginning, but it's not a huge difference. And it's not like the signal is really noisy or anything when it's towards the inside of the disk. So why is it having trouble decoding the signal? Let's just do that again. Signal is stronger, and it starts to get weaker and weaker. But again, totally normal. I move the heads back to track 0. Let's look at the signal now. There's definitely a lot more amplitude here, and it doesn't seem quite as noisy. There are these little bursts in there, which actually might be coming from this cheap power supply that I'm using here. I don't know how good this thing is, and yeah, it's a pretty cheap thing. So this could be noisy itself. I think what I'm gonna do is I'm gonna grab the large ATX power supply with the 286 board, and we're gonna try to read and write some real disks on this disk drive. All right, the floppy drive is connected to my 286 board through a normal floppy drive controller. I'm using the same cable and everything. Let's take a look at the disk. This is one of the ones we formatted, I think, on that computer or maybe this computer, August 2024. So that works. Let's try using scan disk on the A drive. There's no files on here, but maybe we can do a sector scan on here. Surface scan, that is. And even though it's configured as 360K in the BIOS, it doesn't actually cause any kind of issues because the file allocation table describes whether something's on head 0 or 1. So it will completely work perfectly as a single-sided drive, even configured on the motherboard as a double-sided drive. If this finishes without errors, which it seems like it did, we're going to go into IMD next. IMD, or image disk, is a tool I absolutely love to use. We just need to change this to 4D tracks, single-sided, double step is off. And now we can go to align, and we should be able to jump around to different parts of this disk here. And we can listen to the tone it's making. That particular pitch is telling us it's reading all of the sectors properly on this disk. So we can jump to track 30. It's fine, you have one beep that's a little bit lower as it seeks because it loses track of where it is until it resynchronizes. And we hit the plus key and we're going to go up all the way up to 39. And we are at 38. And there's 39. So a real floppy controller and DOS is having no trouble reading the disk that's in here, even repeatedly reading track 39, which when we were using the Greaseweazle was creating a few little errors like that. I'm actually not 100% sure why the Greaseweazle was having trouble reading this disk. Let's try creating a disk image using IMD. We're going to read data or read disk into file. It's R command, and we'll just do test 180 here. Test 180, test 180K. And just hit enter, and this is going to read the entire disk in. And since I went into setup, I configured it as a single-sided disk. It's not going to try to do both sides. And let's see if this has any trouble reading the sectors in those tracks near the top of the disk. 0 errors, and it didn't even pause or make any seeking noises or retries or anything like that. It just freaking worked. What I'm curious if we can sys the A drive, and maybe we can actually boot off the A drive with DOS 622. It might not fit. I don't know if DOS 622 needs more than 180K or whatever the formatted capacity of this drive is. Certainly sounds normal with the seeking. It's nice and quiet too, this particular drive. Invalid media type. So we're gonna do format A/F, and we gotta specify the size because DOS thinks this is a double-sided drive based on the BIOS /S/U for unconditional. And let's see if this works. Looks like other valid types are 160 kilobytes or 320. Interesting. Track 0 unusable. All right, we're going to use N format here. We do need to change this to just single-sided here because it defaults to double-sided. Let's format this disk here. Oh boy, what's happening? Is the drive not working now? I actually don't know what's going on here. Feels like the drive broke again. Just making sure the cable's all connected correctly. We just made a successful disk image in IMD, and it was fine. And now, doesn't look like we're able to read the disk anymore. What happened here? What freaking happened? So let's go to alignment tool here in IMD. Let's just see what this shows now. What's happening here? I've never heard IMD kind of go crazy like this. Oh, wait a second. Wait a second. I jumped to track 30 and it's fine. 0? So something weird happened on track 0. Something got written and it's confusing DOS. And let's do this again and hit the P for parameters, format parameters. Okay, sectors per track, 9 is good. Yep, 250 kilobits, MFM, 512. Okay, so this is a typical, I'll just write AA onto there. And now we'll hit F. That's for track 0. It's not working. I've honestly never seen IMD behave in this way. This is very strange to me, and I don't quite get it. All right, well, I went ahead and I hooked up the working disk drive we were testing earlier, and it doesn't work in the same way either. So it's not the Tandon drive that's the problem. It's something with the setup here. And I've actually replaced the controller. I'm using a different controller, so it's not the controller. The cable's the same, power supply's the same. I don't know, I'm completely confused. But if I try to write the disk, which is not working obviously, and if we go to align disks, we're gonna get that same random wild beeping noise, even with this other disk drive here. So it's not this one at all. Some of the tracks work. If you jump to another track that's, oh, okay, this disk got erased. Let's put in a disk here that actually has a format on it. Oh, I don't know, now it's not reading anything. It's very strange. So I just put in a disk that I know I just formatted on the other computer there. It should be able to read it, hopefully, properly. Or not. What is happening? This is very confusing. This thing is acting very strange. I'm just gonna switch to a different motherboard entirely. I don't know what's going on with this one. Well, would you believe it's the motherboard, I guess, because I've switched over to my 36SX and I'm formatting the disk in the drive I just fixed, and it freaking finished. And I don't think it actually, yeah, not enough room for system files, but it made a readable disk. Let's try copying a few files onto it, whatever's on the root of the C drive here. We'll just copied onto the A drive. I'm just flabbergasted. I don't think I've ever tested floppy drives on my new favorite 286 motherboard, and for whatever reason, it just, I mean, I'm assuming it works fine with 360K drives, but for 180K drives, nope. And look, it's copying these files over. Although what just happened? It looked like it just froze. You know, maybe this is all my fault where I said, oh, 180K drives, they work fine on DOS. You know, no problem. No issues whatsoever. I don't know. Now it just froze again. Is this the... Oh, but I think it's the computer that froze because I can't even push Control-Alt-Delete. If this were just a problem reading sectors, I don't think it would have froze like that. Sometimes these retro computers are really fussy. And this is a perfect example of ultra fussy. Let's try end format here. So we'll just edit this, change it to 1, and we'll try to format this disk. I couldn't get this to work at all on the 286 board. It would always just error out on that first sector. And obviously it's working fine here. Or so I thought. What is happening? It just froze. I can't push Control-Alt-Delete either. I wonder if this is a problem with the XT IDE BIOS on here, because it does patch some floppy drive stuff here or something. So let's switch back to the 8-bit XT IDE and the other floppy controller. Let's see if this makes any difference. I mean, could still be this as well as the 286 motherboard causing issues. So here we go. Let's try 180K. And disk is write protected. What did I do wrong? I had it actually 1 row of pins off there. I think that was the problem there. Yeah, it was making the drive spin all the time. That should have been the clue that there was a problem with the cable. Okay, here we go. Let's try one more time. I don't think that freezing on cylinder 17 had anything to do with this disk drive. There's no way that a floppy drive could freeze the whole computer like that. Okay, so it's going further now. Now, when I was using this controller, I was also using my XT IDE BIOS that was on here that also has the test RAM utility on there. Maybe that causes some kind of an issue. I don't know. But we did just get a good format out of the disk here. Let's try copying some files onto it again, because that's what froze up last time. I was honestly starting to believe that there was something wrong with this drive still, and I would have to do another repair where we have to dig into some kind of a write issue with it. But clearly that's not the case. What we can do here is back in IMD, let's do an align, and I'm gonna do that format command again. That would make it go wild and say 255. Okay, all looks good there. So we get to set up the parameters here. And there we go, and I hit F. This is where it would go, yep, it's fine. No issues. So we could format the tracks. So there was something with that other motherboard that was absolutely causing this thing not to work. And we can do this one more time, /F:180. This is right from DOS. And, oh, I forgot the /U. Yeah, okay. All right, so the drive is fixed. It is absolutely fixed. And at the end, it was very touch and go, but it turned out that it was this motherboard here causing all my issues. So I really need to dig into this a little bit further and do some diagnostics, I guess, on here, trying out floppy controllers to see what exactly is going on and why single-sided drives just seem to cause all sorts of random issues. And then not to mention, I guess with this ROM in there, I don't know, it's also causing issues with the whole computer freezing. It's gotta be this, I don't know. And then I guess with this controller or the XT IDE BIOS, this also has issues. Now I have to admit, I never really use this card with the floppy controller. I'm always just using it with the compact flash card on the IDE port. So 2 different problems here? I don't really know. But what I came here to do in this video, which is fix this floppy drive, I was able to do. And this drive now is fully fixed. And we got down to the bottom what the problem was. Whoa, That was that chip which I just dropped on the floor. And hopefully you learned a little bit about how floppy drives work. So if you have a drive like this that is mostly working but then can't seem to read or write, you have ideas about how to dig around and start to troubleshoot things. So with that said, I hope you enjoyed this video. If you did, I'd appreciate a thumbs up. But if you didn't, you know what to do. Subscribe, all the other YouTube junk. And a huge thanks to my patrons. Their names are going up the side of the screen. They make it possible I do this full time, and I think that's going to be that. So stay healthy, stay safe, and I'll see you next time. And I need to make sure I pick up this chip here because I don't want to get this embedded into my feet. Yeah, I'm just wearing socks down here. So yeah, there it is. All right, see you next time. Bye-bye.